Welcome everyone. It's my great pleasure to introduce Dr. Elina Robeva. The short story is, while I was a postdoc, I was described this fascinating problem called the graceful labeling conjecture. And by the way, it's the other way of getting an A in my graph theory class, if you can solve it. And what I've learned about the bare basics of graceful labeling is by reading Elina's undergraduate work on the topic. She had outstanding notes back then, and I decided to follow her regularly. And she ended up working on things that I'm interested in. So I follow Elina's work, and I've been a big fan. So Elina graduated from UC Berkeley and in 2016, and is now instructor of statistics and NSF postdoctoral fellow at MIT. She'll be talking about maximum likelihood density estimation under total positivity.
Thanks so much, Elina, for having me here. It's been really nice. This has been really nice so far. So today I'll tell you about some recent work that has been going on in collaboration with Bernd Struffels and Caroline Uller. So we're doing maximum likelihood density estimation under total positivity, and I'll explain what all of these are. Right, so first I'll start by just saying a couple of words about density estimation. So the main problem is that we're given i.i.d. samples x, so those are points in Rd, from an unknown distribution on Rd that has a density p, and we would like to estimate the density p from the samples, and there are two main approaches. One is parametric, where we assume that p lies in some parametric family, and we'd like to estimate the parameters. And so this is very nice to do because usually the parameters are finitely many, and so this is a finite dimensional problem. But on the other hand, it's sometimes too restrictive because maybe the real world distribution where our samples came from is not actually coming from this family. And on the other hand, there's the non-parametric approach where we assume that p lies in some non-parametric family, which is what we'll be doing today. And for example, we can impose shape constraints. And the reason I'm giving this example is that that's what we'll do. So the shape constraints could be that p is convex or monotone, increasing, or something like this. And however, this is an infinite dimensional problem because the set of convex densities is an infinite dimensional set. And moreover, we have to be careful how we select the constraints because they have to be strong enough so that there's no spiky behavior. So if we didn't impose too many constraints, then density estimator will just be a sum of Dirac delta functions above the samples, and that's not something that we want to find. And then on the other hand, we want to have constraints that are weak enough so that the function class is large and contains, hopefully, the distribution that the samples came from. Okay. So, as I said, we'll be talking about shape constraint density estimation, and just as a quick overview here, some types that have been done before. So people have studied monotonically decreasing densities, convex densities, log-concave densities, which is something that I'll actually talk about a lot during this talk, and also generalized models where the density is assumed to be a sum of functions that are monotonically decreasing, convex, and log-concave, and then we'll try to estimate. Okay, and so in this talk we'll impose a different shape constraint, which will come from total positivity. So we have that, and on top of that we'll also impose log-concavity. Right, so now I'll tell you what I mean by total positivity. So, in fact, by totally positive, I mean multivariate totally positive of order 2. It's quite complicated, and that's why we just say totally positive in the title. So, a distribution with density p on a subset of Rd is multivariate totally positive of order 2, or for short MTP2, if the following inequality holds. So for every 2 points in our space, p of x times p of y is less than or equal to p of x min y times p of x max y, where these are coordinate-wise minimum and maximum. Okay, so if you have R2, then you have x here and y here, then this is the minimum and the maximum, so p of x times p of y is less than or equal to p of this times p of this. That's the definition. And then, okay, and so if you are familiar with supermodular or submodular functions, then this is the same as saying that log of p is supermodular. Okay, so, or p is log supermodular. All right, so MTP2 is a strong notion of positive dependence. In particular, it implies positive association. So what is positive association? A random vector x taking values in Rd is positively associated if for any non-decreasing functions phi and psi, the covariance of phi of x and psi of x is non-negative. So, for example, phi and psi could be just phi of x could be xi and psi of x could be xj. So clearly the covariance between the coordinates is non-negative, but it's a stronger condition than that. And it turns out that MTP2 implies positive association, and moreover, it has nicer properties than positive association. That's why we're going to look at it. Okay, so what are some properties of MTP2 distributions? If x is an MTP2 random vector, then any marginal distribution will be MTP2. So if you marginalize one or more of the components, then it will be MTP2. And if you condition on one or more of the xi's, it will remain MTP2. So that's really nice. That's like Gaussians. And what's also nice, like for Gaussians, is that xi is independent of xj if and only if the covariance of xi and xj is 0. Okay, and actually this third condition holds for positively associated random vectors as well, not necessarily, not just for MTP2. Okay, and then there's also another way of, maybe simpler way of defining MTP2 distributions. That is that if the density is positive everywhere, or there are actually a bit weaker conditions for this, then P is MTP2 if and only if it's MTP2 whenever you restrict to two coordinates. So if you just impose that the condition from the definition, this one here, holds whenever x and y are equal except in two of the coordinates. Okay, so then that's enough. If you that will mean that the whole distribution is MTP2 if, for example, it's positive. Okay. So here are some examples of MTP2 distributions. So if we take a Gaussian random variable with mean mu and covariance matrix sigma, then it's MTP2 whenever sigma inverse is an M matrix. In other words, its off-diagonal entries are non-positive. So, so this in particular implies that the off-diagonal entries of sigma are non-negative. So the covariances are all positive, but it's a stronger condition. So you can find matrices sigma for which the whole matrix is non-negative, but its inverse is not an M matrix. Okay. And another example would be, so this is supposed to be a graphical model. So suppose you have a hidden variable, z, and some observed variables, x1 through xn, such that the xi's are independent given z, and moreover, each xi is positively correlated with z. Then one can show that the joint distribution of the x's is MTP2. So a particular example where this could show up would be if z was the IQ and the x's are scores on an IQ test that increase if you answer the question better, so they're positively correlated with the IQ, then the joint distribution is MTP2.
And it's all without assuming that the joint distribution is Gaussian.
Right. Okay, and then the last example, so the last bullet point here is a bit of a vague statement that says that the more conditional independence relations between the variables there are, the more likely it is that its distribution is MTP2. So you can imagine a setting where we have, let's look at just Gaussians, and we look at 3x3 Gaussian covariance matrices. So only 5% of those have inverses that are M matrices. But now if you look at covariance matrices for which x1 is independent of x2 given x3, for example, then 25% of all such covariance matrices will satisfy that their inverse is an M matrix. And then if you impose an additional independence relation, like x2 is independent of x3 given x1, then you get 50%. And then if all xi's are independent, then you obviously get a diagonal matrix, and that's MTP2 because its inverse is also a diagonal matrix. So its off-diagonal entries are not positive. Anyways, these are some examples. And so this is what we're trying. So this is the type of densities that we'll be trying to estimate. Okay, so going back to our problem, we are given i.i.d samples x in our D, and we're also going to have weights. So you can think of them as being 1 over n for each sample, but maybe for some reason you have different weights on the samples. And then we would like to estimate p. Okay, so we'll be maximizing the likelihood, or the log likelihood. So the log likelihood of observing points x with weights w, if they're drawn i.i.d from p, equals to the sum over I of wi times log of p of xi. It's just the log likelihood. And so our problem is maximize this function subject to the constraint that p is an MTP2 density. Right? And however, this problem, as defined this way, is actually, yeah.
So what are the weights for?
Yeah, so you can think of them as 1 over n, but you can also maybe you observed several things around this point and you just put them together as one point or something. You make weights. I mean, so the theory just works with weights anyways.
Yeah.
Okay, so this problem is actually not well defined. So you can find a sequence of densities for which this goes to infinity, and they're MTP2. So here's
Do the wi's have to add up to 1 because
yes.
Because it would seem the natural thing, like for the actual log likelihood, wi's would be identically 1, not 1 over n.
Yeah, I mean, we're keeping n
Well,
fixed.
it works if they don't add up.
What?
What's that?
It's fine if it, I mean, we're keeping n fixed, so.
You can always normalize it.
No, I understand that. Yeah.
Yeah. Sorry for the question. Sorry.
He's
I'm usually the worst behaved.
He's my apologist.
No, my question.
But they do have to be non-negative.
Yes, so I guess, yeah, so you're saying they're not.
Oh, yeah.
negative. Yeah, sorry, I should have said that. Yeah. Okay, so as I said, this is actually not well defined because we can find, I mean, basically you can put Dirac delta functions at some specific locations, but here's a simpler maybe example. So suppose we observe 2 points, x1 and x2 in R2, so here they are, this one and this one, and now we'll construct a sequence of densities that are MTP2, but the likelihood goes to infinity if you switch between these densities. Okay, so here is the first one. We have 2 rectangles, so it's 0 everywhere else and some constant on these 2 rectangles. So it's very easy to check this MTP2 because there's several options for where x and y can be, but if it's like this, then the product of these 2 is 0 and the product of these 2 is also 0, so you're fine, and then there are several more choices, but you can easily see that the MTP2 condition is satisfied with equalities everywhere. And so, and now just take these rectangles and shrink them. So if you shrink them, you have to increase the weight there to make it integrate to 1. And then you can keep shrinking them, and the weight will go to infinity. And recall that in the likelihood, you're actually summing. You're summing over the values of p at these points, so the likelihood just goes to infinity. Okay.
But the limit is interesting because it's 2 vertical segments, so is it really always there's no?
I mean, it's not that. You can actually just take Dirac deltas on these 4. So you can just whatever your samples are, you can take the grid with these that they generate. Like if you have these, then you can add all the possible grid points. or just add all minima and maxima and then.
But the Dirac delta is not a solution because you want a density at the end, right?
Yeah, it's,
Okay.
so we're not happy with this.
Okay.
But that's not a bad solution, creating the grid.
Yeah. I mean, yeah, but we are assuming that it's coming from something else. Okay, so to remedy this, we actually decided to impose another constraint. So as I was talking in the beginning, sometimes you need to have strong enough conditions so that this behavior doesn't happen. And we chose to impose the constraint that P is log-concave. And you know, there are probably other ways to do this, but we chose this one. So a function is log-concave if its logarithm is concave. And so it's kind of a natural assumption because it ensures the density is continuous. And then there are many known families of parametric distributions that fall into this category. So here are a few. And in particular, the Gaussian with its inverse covariance matrix being an M matrix is still one of these. So that's fine. And then as a bonus, maximum likelihood estimation under log-concavity is a very well-studied problem, and there's a lot of theory that we can actually use and try to see if we can prove the same results that hold for log-concave density estimation.
I have a question. There's a famous theorem in one dimension that says that a log concavity is equivalent to something called strong unimodality. You know, that you convolve with any unimodal distribution, you get a unimodal distribution. Is there an analog to that in the multivariate situation you're working with?
Yeah, I'm not familiar with it. Okay, so now I'm just going to actually review some of the known theory about log-concave density estimation. It's a very nice theory, and as we'll see later, we're going to try to see if we can prove the same things. Okay, so now we'll just focus on the problem where we're maximizing our likelihood subject to P being a density and it being log-concave. So there's no MTP2 here. And there's a very nice theorem by Kuehl, Samworth, and Stewart who proved that with probability 1, a log-concave maximum likelihood estimator P hat exists and is unique. Okay, and moreover, the logarithm of P hat is a piecewise linear function. It's called a tent function, supported on the convex hull of the data. So this is the data on the bottom, and then on the top we have a tent function. And the way you get this tent function is you have a height above each sample point, and then you imagine having poles with this height, and then you put a tarp above all these poles, and you make a tent. So, and that's a piecewise linear function. And it's the regions where it's linear are polygons or polytopes with vertices coming from the samples.
And that's a general D.
Yeah, exactly. Yeah. And so here is a more precise definition. So given points x with heights y, so these are the heights of the poles, the tent function hxy is the smallest concave function, such that at xi, it's bigger than or equal to yi for every I. So it's exactly this thing where you put a tarp on top, and there's equality if the tarp is touching the tent, is touching the pole. Okay, and then therefore P hat is actually going to be x of hxy for some y. And now instead of, so this is their theorem. The theorem said that for the MLE, P hat, its logarithm will be of this form. So instead of searching over all possible log-concave densities, you can just search over these. So the original problem was maximize over P, over likelihood, such that P is a log-concave density, and that's an infinite dimensional problem.
Did they do that with that proof? Is that a method of Sid's proof? Do you know?
The proof is actually very simple. I'm actually going to tell you the proof.
Thank you.
Okay, and then, okay, and now because P equals x of hxy, then we can just substitute it for over there, and that becomes a finite dimensional problem because we're now maximizing over all heights y of this likelihood such that x of hxy is a density, because we already know that it's log concave. Okay, and now we can cancel the log and the x over there, and we get sum over I of wy I hxy of xi. But remember that hxy at xi is bigger than or equal to yi, and we can actually just substitute that with yi, because there's equality doesn't happen only if the height is below the 10, and you can just assume that all heights are touching the 10. And so here we now just have a linear function that we're maximizing such that the exponential is a density. And so the exponential being a density means that the integral is 1. And there's this very nice convex analysis trick where you can just subtract this integral, and at the optimal y, you can show that this integral equals 1. Yeah.
Sorry, just one thing I'm missing, which is that if you have one of these 10 functions, doesn't it? Oh, so this is the log of the function that you're talking about?
The 10
never mind.
function is the
I was
log.
worried about it going negative. Okay.
Yeah, so actually, in the 10 function, it's minus infinity outside the convex hull. You can imagine that the torque goes
Gotcha.
Okay. Because then when you take x, it becomes 0. So the support is just okay, so now we're maximizing this function. And as I said, so what happens is if you can prove that the integral equals 1 at the optimal y. And the way to do this, you can suppose the integral equals some constant c, and then just rescale everything to make it 1, which means you have to subtract c from each of the yi's. And with this new heights yi, where you subtracted c, you can see that the difference between this and the value of this function at the new yi's is equal to something like c minus 1 plus or minus log c or something like that. Or maybe c. Anyways, it's a function like this, and in order, because you assume that the y is more the maximum, and this function is always positive. So this function is always negative, but it has to be positive, so it turns out that c has to be 1. So I mean, it's you can do it. It's not very hard. So you can prove that the integral has to be 1. And so therefore now we have no constraints. We just are maximizing this function in y, and it's actually a concave function. So it's not a differentiable function. So they use subgradients, and you can write an algorithm that maximizes this function. Okay, so this is how log concave density estimation is done, or that's one way. All right, so going back to our problem where we had log concavity and MTP2. So we're going to try to answer a similar question. So first of all, does the MLE under log concavity and MTP2 exist with probability 1, and is it unique? Then what is the shape of the MLE? So first of all, what is the support? We saw the support for log concavity is the convex hull. Is this the same in this case? And also, is the MLE always the exponential of a 10th function, the way it was for log concave density estimation? Which 10 functions are allowed, and can we compute it? And so, going back to this, which 10 functions are allowed? Recall that P is MTP2 if and only if its logarithm is supermodular. So if P was the exponential of a 10th function, then you would need this 10th function to be supermodular. Okay, so, and it turns out that not all piecewise linear concave functions are supermodular. So we have to see which ones are even allowed. Okay, so we'll start with the first question. So existence and uniqueness, we were able to prove the same result. So the MLE under log concavity and MTP2 exists and is unique with probability 1. So the only difference is that our proof actually is very different from the log concave one. It just uses convergence properties for log concave distributions, like all of this theory that already exists for log concave distributions, and doesn't actually shed light on the shape of the MLE. whereas the proof for log-concave density estimation directly shows that the MLE is a log function. So I'm going to go over it in a bit. So our proof doesn't shed any light on what the MLE should be, right? So you want to see what it is. Okay, and so the first step will be figuring out what's the support of the MLE. So consider the following samples in R2, and if we're just doing log-concave density estimation, then the support is going to be the convex hull, right? But now we also want a density which is MTP2, and so what would happen if we had this one? Then if we chose this to be x and this to be y, then we want p of x times p of y to be less than or equal to p of this point times p of maximum, and this can't be 0. So we have to add this point and also the one on the upper right is the maximum of 2 points. So the support has to be something called the min-max convex hull. So it's min-max closed and convex. And right, so we have two notions here. One is MMX, which is the smallest min-max closed set containing x. So this is a finite. If x is finite, this is also finite. It's just some grid points or something. So right, so if x and y are in the set, then their coordinate y is minimum and coordinate y is maximum are in that set. Okay, and then there's the notion of the MM_conv of x, which is the smallest min-max closed and convex set containing x.
I have a question concerning the computation of MMX. So if you start with an S that isn't closed undertaking mins and maxes, and then throw in the mins, does that finish it, or
Yes.
so one stage is enough to?
One stage is not. Oh no.
That's what I was
one
asking.
stage is not enough.
Oh, it's not enough. Then is a finite number of stages enough?
Yes.
Or? Okay.
So yeah, because you can imagine that first of all, so if you consider all possible grid points, each of whose coordinates equals to the same coordinate in one of the points of x. It's not very good way to say it. Like, so there are 3 possible x coordinates or y coordinates, these 3, and then there are 3 possible x coordinates.
Yes.
And so if you just take this grid, that is min-max closed. So that's enough, but maybe that you don't need all of it. Maybe you can shave off some stuff. Okay, and the reason I've defined both of these sets is that maybe we can construct this one using this one. So that's what I thought. So how can we find, so the support equals MM_conv of x. So it's the smallest min-max closed convex set. So just to make sure that it's clear, so the reason it's convex is that our likelihood has to be log-concave, so support has to be convex, and then it has to be min-max closed. Okay, so how can we find this MM_conv? And my intuitive thought was to just find MM of x and take a convex hull. Okay, so this is just a proposal, which will actually turn out to be wrong. So, but I thought it was right for a long time. So and so how do you find this MMX? You start with x and then you keep adding points. So you can add some points, but then so the orange ones are all possible minimum and maximum of the black ones, and now there's one missing, and we have to add it, and now we're done. So this is a min-max closed set.
Is it unique? Is it unique?
Yeah.
The MM of x is...
Because if you take intersection, so take all closed sets, then you just take it.
Okay, and now my idea was to just take the convex hull. Okay? And the question is this now both min-max closed and convex? And in this case, it actually is true, so this can't really, it's not a counterexample. But in general, it's not true, okay? So, and the reason that it was hard to even think about it is that it's true in R2, and if X is a subset of the vertices of the unit Q, but it's not true for higher dimensions, okay? So, so here is a counterexample. Suppose we take these 4 points in R3, this is our x, and this set is min-max closed because the points are in order. There's no, so for any pair of points, one is the minimum, one is the maximum, so it's min-max closed. And we have this inequality. But the convex hull, which is just this tetrahedron, is not min-max closed. So here is a point. So let's take the maximum of 640, I don't know, maximum of this point here, and 633/2, which is on this line, 3/4 of the way. Then that equals 643/2, and it's actually a little bit outside.
But it's intriguing that this is labeled lemma. So, like, is this going to actually lead to something
yes.
general?
So
wow.
now I'll tell you how to find the min-max convex hull. Yes. So,
Gives you a lemma, that's still nice.
okay, so there's a theorem called the 2D projections theorem, which dates back to the 70s, and most authors attribute it to George Bergman from Berkeley. So for a finite subset X, the min-max convex hull of X equals the following. It looks complicated, but maybe it's not that complicated. So you choose any two coordinates, I and j, and you project onto the ith and jth coordinate. And then you do what we did in the previous slide. So, I mean, you can just take the min-max closure of X to begin with, and then project on the ith and jth coordinates. Take the convex hull of that. So what I mean by project, you just take the ith and jth coordinates of the point, take the convex hull, and then you take the pre-image, which means it's kind of like a cylinder. Okay? Yeah, so you take all possible points that have these ith and jth coordinates, and then you intersect for all I and j. And so you intersect these cylinders, and then you get the min-max convex. And we know that each of these sets here is min-max closed because it's in R2. So, okay, and actually, if you think about it, this means that all of the inequalities defining this convex polytope only have, so all the inequalities defining it only include two of the coordinates. So every inequality includes some I and j for I not equal to j. Okay? And a different way to describe min-max convex polytopes is the following. A subset in RD is a min-max closed convex polytope if and only if it's defined by a finite collection of bimonotone linear inequalities. So what are those? A linear inequality is bimonotone if it has this form. So it only has two coordinates that are non-zero, ai xi plus aj xj plus b less or equal to 0. And if they're both non-zero, then you want them to have opposite signs. Okay? And so in this picture here, that means that in R2 you just need lines